Hello everyone and welcome to the another session from the ScholarGate and PetroNile Academy. My name is Nitin from ScholarGate and today's session covers an interesting topic which is engineering project management in oil and gas presented by Mr. Freeman Dugu. Mr. Dugu is a project management coach with over 13 years experience and certification in project management, project risk management, and a CORE in licensed engineering. Before we start, I would like to remind you all that there will be a Q&A session in the end, so kindly write down all your questions in the chat box. Mr. Dugu, the mic is yours.
Hello, everyone. My name is Freeman Dugu. As Mr. Nitin has said already, I'm an engineer and a project manager. I've been a project engineer in the past, and yeah, my experience covers a wide variety of projects. So, um, currently, I'm working on a refinery project. I'm working in a company where we're building a refinery, a 650,000 barrel capacity refinery. In the past, I've worked on the front end engineering of a very long and complex pipeline system. I've been a project manager on a bitumen extraction project. I've taken part in some offshore field development projects and some onshore pipelines as well. I have my degrees in subsea engineering and civil engineering, and I'm PMP certified for 10 years now, and risk management certified. And yes, I'm a licensed professional engineer in Nigeria. So this presentation is actually taken from my course, a course that I am about to launch, which actually addresses the very topic that we're going to be discussing today. And that is engineering project management, which is management of engineering projects, management of engineering projects in the oil and gas industry. So in that course that I'm about to launch, I expect that the course will be, it will be useful to professionals that are involved with projects in the oil and gas industry and other industries as well. Because if you are in the project management business in the oil and gas industry, you find that a lot of things that we do in the oil and gas industry are quite similar to the way projects are managed in other industries like petrochemicals, like beverage manufacturing, and so on. So early career engineers would benefit from this course and what we are going to discuss today. All kinds of engineers, process, mechanical, civil, electrical, instrumentation, and safety. Early to mid-career project engineers. Now, some engineers straight from school, they get employed as as project engineers or junior project managers. So it's good for them to have a background in the way projects are managed in the industry. Project planners and project controllers, project schedulers, they also have, they would benefit from this kind of discussion. And then construction engineers and managers as well. So as I said, these slides are from the course. Sorry. These slides are from my course, the introductory portion of my course. And in that course, I expect to lecture everyone on who does what when you're managing a project, because the job of a project manager is basically to direct other moving parts of the project, is to get something done through someone else, through a group of other persons. So understanding who is responsible for a specific type of job is very important. Understanding when a certain deliverable should be ready, when a particular type of work should be completed, is also very important. And then having an understanding of how that job should be done is also very important to the success of a project. So, in the course, this is not what we are going to talk about here today. I'm only going to talk about the introductory aspects. But then, in my course that is coming up, there will be an overview of project engineering, which is what we are talking about here right now. But then I would also talk about process engineering, what the process engineers do on projects like this, regardless of the industry. It can be oil and gas industry, it can be beverage manufacturing industry, it can be pharmaceutical industry. The general philosophy is, more or less the same. I'll talk about the role of the mechanical engineers, piping engineering, safety, civil engineering, materials and corrosion, instrumentation and control, electrical, and then the actual uh, management of the project, the concepts that go into managing projects in the oil and gas industry. So this next slide is not very relevant here, but for for persons who would take my course, I would encourage them to have a pen and paper to take notes. So let's go into the topic of discussion of the day, an overview of project engineering. Just to confirm, is everyone still hearing me? Because it's quite silent, so I want to be sure that I'm not talking to myself.
Yeah, it's audible.
Okay, very good. So, now, first and foremost, when we talk about overview of engineering project management, this we called this topic, the topic of this discussion, an introduction to project management. Mr. Newton, can you remind me what we called it? An introduction to project management in the oil and gas industry. Is that correct?
Yeah.
Okay, fantastic. Now, project management in the oil and gas industry proceeds in three phases. First, there is the engineering phase, and in the engineering phase is where you design the facilities, you produce the various lists, like list of equipment, list of lines in the facility, instruments and utilities in the facility. You produce the data sheets, that's the mechanical and process data sheets. You produce drawings that are needed for fabrication and for the erection of the equipment and piping at the site. That's basically the role of engineering. That's a brief summary of the things you expect to achieve in the engineering phase of a project in the oil and gas industry. Then comes the procurement phase. In the procurement phase is where the procurement professionals, they purchase the equipment, such as mechanical equipment, pressure vessels, heat exchangers, and so on. They purchase equipment and materials. When you talk about materials, you're referring to things like pipes and cables and so on. As I was saying, in the procurement phase is where we procure the equipment and the materials that were designed by the engineering phase, right? And then we have the construction phase where we basically go to the sorry, where we go to the construction site and we erect the equipment and the materials that were purchased by procurement according to the designs and specifications of engineering. So the focus of our discussion here today will just be a brief summary of what actually happens in the engineering phase. We'll not go through everything because obviously we don't have enough time, and that would be a very detailed course on its own. So the focus is on engineering, one, because engineering sets the stage for everything else that follows. If you get your engineering wrong, then everything else is likely to be wrong because you are going to be procuring based on the engineering design. So if your engineering is wrong, then obviously what you are procuring is also going to be wrong. Similarly, your construction will also be wrong if your engineering is already wrong. So that's why there's a lot of attention on engineering. I love being part of the engineering process of the facility, not as a design engineer, but as a project engineer or a project manager. So another reason why engineering might be very important is cost. the cost of a project, the engineering phase can have a very big impact on the cost of the project, whether that project is going to be very, very expensive, more than necessary, or very, very cheap. It depends on the philosophies that are outlined in the engineering phase. So this is what engineering phase of a project looks like. Engineering as a whole is broken down into the concept selection phase and the basic engineering phase and the detail engineering phase. Now, these terminologies, sometimes they vary from company to company. People call them different things. Like you hear somebody saying pre-feed and then feed and then detail engineering. In some other places, you might hear someone referring to as feed, but they actually refer to the last two sections combined. So, but to keep it simple, there is concept selection, then there is basic engineering, and then there is detail engineering. I'm going to explain that as we proceed. So I have a slide here about why engineering is so important. What I said not too long ago, you can see it here as a picture. On this chart, the vertical chart is the horizontal line, the horizontal axis is your time, how far you have gone in your project. And then these two lines, obviously, one represents your ability to influence the project and the other represents the project costs. So in the earlier stages, assume this is time zero, in the earlier stages of the project, where most of your design, you are just doing it on a computer, the process guys are, playing with the various process scenarios for the facility, be it a processing facility or a production facility. It doesn't matter much. In the early stages of the project, you can basically change anything because on the computer, you can delete one thing and add another thing. You can say, you can simulate 2 wells, you can simulate 4 wells. It basically doesn't cost much. It's just something that you're doing on your system, so it is cheap. Now, as the project progresses, your design advances, something is designed, and then that design is the basis for further design, and then that becomes the basis for further design again. Once that complexity adds on top of further complexity like that, eventually, obviously, you're going to start procurement. You're going to start placing orders for your compressors, for your separators, and so on. So when you start placing orders, making changes to the project at that point can become very expensive. So you can see this red line here. Can you see my cursor and my screen?
It's visible.
Okay, yeah. So as you progress from time zero to time X, the cost of making changes to the project gradually increases. And at a certain point, it increases at a very high rate. That's the point where you have started your procurement and you may have started some site work already. So when you're already at site constructing, you cannot suddenly say, oh, well, you can, but it will be a very expensive decision for you. If you decide that instead of one compressor, maybe you need 2 or 3 compressors along a particular pipeline, that obviously would have a lot of impact. Now, if that scenario was considered in the beginning, when the entire project was basically on the computer, it would be easy to delete and add and run the simulations and make the appropriate decisions. So the ability to influence the success of the project reduces, because when the stakeholders of the project sponsor, they have already spent more money and you are telling them they need to spend more money, they are reluctant to do that. So influencing the project later in the life cycle of the project is more difficult. That's what these 2 lines here represent. Initially, you can have a high level of influence, but with time, the influence goes down. Initially, the cost of making changes is very low, but then it goes high. So let's look at the project life cycle. This is what it looks like. First of all, there is a business appraisal phase where an opportunity has been discovered and then that opportunity is investigated. The aim of this phase is to create a business case and even to compare, because in the earlier stages of the of an enterprise, let's call it an enterprise for now, you have not yet decided whether you want to do it as a project or you want to go into a merger with another company to achieve your business goals, or you want to acquire a company that is already in existence. Let me use an example. If you want to, if you realize that in a particular country, they have need for finished products like petrol and kerosene and so on, you have to decide, you have to do your analysis to decide whether you should build a refinery, as a project, or you should go into a merger with another company that already owns a refinery and then maybe upgrade it, or to acquire that company. All of that is done, all of that analysis and decision making is done in the business appraisal phase. And at this stage of the project, you have only you have the owner's core technical team, because even though it's a business decision, the people taking the business decision, the business executives, they need input from some highly experienced technical guys in order to be able to make that decision. So it's a techno-commercial stage of the project. Then once the decision is made to go forward with the project, then you go into the concept selection phase. In the concept selection phase is where you validate the business case that was proposed in the beginning, and then you come up with a scope of work, because you have you have already run some simulations. You have come up with a basic scheme for which the facility is going to operate based on, and then based on that basic scheme, you can come up with a scope of work for the front end engineering design. That's the basic engineering, and then maybe even some scope of work for the EPC phase of the project. Another deliverable that you expect from this stage is the basis of design, because you have decided that you're going to go ahead and build this project. You have created a scope of work to achieve what you want to achieve. Then the technical guys also have to come up with a basis of design that will guide the design work that is going to be performed. And then, of course, at the end of this stage, you also select the design contractor. When you select the design contractor, then the feed stage starts. Feed means feed here, for those who are not familiar, it means front-end engineering design. Another word for it is basic engineering. So the concept that has been selected for the facility in the concept selection phase is then further developed. All the aspects of the design are taken care of. The electrical design, the instrumentation design, the mechanical design, piping, safety, all of that design happens in the feed stage of the project. And then after that, you expect to have deliverables like there's something called the feed package, where you find all the P&IDs, all the plot plans, all the line lists, the process flow diagrams, the data sheets, everything that you need to conduct procurement is produced at the end of feed. And then at the end of the feed, you also have a definitive cost estimate, a cost estimate that the business decision makers are going to use to make a final investment decision on whether to go on with the project or not. So this tells us something very important. All the work that is done from business appraisal to concept selection to feed the entire front-end engineering design, all of that is part of project planning. The management of the company or the government that is to do the project has not yet decided whether they want to do that project or not. It is at the end of the feed, when everything has been defined, when they know all of the equipment that will be present and the cost of those equipment within a plus or minus 20% error margin, then they can decide whether they want to do the project or not. So a project has not really taken off until the final investment decision at the end of feed is made. Now, this is usually confusing for some people, because sometimes all of these stages, the business appraisal phase, the concept selection phase, and the feed stage, they are substantially expensive. For a project that is going to cost about, say, $5 billion, yeah, if a project is going to cost $5 billion, you can expect all of this to cost about 3% of that amount. So 3% of that amount, is about $150 million, and that is a lot of money for a lot of companies. So a lot of people struggle with the fact that you have already spent $150 million, but you are deciding not to do the project. But then it's just the way it is. It's better to spend $150 million and then realize that the project is not a feasible project and put it on hold, than to spend the complete $5 billion and later realize that it's a project you should not have done in the first place. So everything, the engineering phase of an oil and gas project or any industrial project, is that phase is still part of the planning of the project. It's not part of the project itself. It's not part of project execution. It's only part of project planning. So when the final investment decision is made and that decision is positive, in favor of going forward with the project, that is when you move into the project execution phase. In that project execution phase, you then complete some of the leftover engineering work that was not completed here, can then be handled by the EPC contractor, the contractor who is going to be responsible for the construction, the actual construction work. Mind you, engineering contractor might be separate, and that engineering contractor will then give deliverables to the EPC contractor. That's the construction contractor, who will then go ahead and complete some engineering, handle procurement, handle construction, installation, and pre-commissioning. I did not say commissioning because, as I understand it, in the standard way of running these projects, pre-commissioning is where project management ends. When you commission the project, commissioning and startup is usually part of operations. So it is not the project team that commissions the facility. It is the operations team of that facility that is supposed to commission it and start up and then continue. So project starts let's say project starts from business appraisal, concept selection, feed, and then goes through all of this detailed engineering, procurement, construction, installation, and pre-commissioning. Once pre-commissioning is done, then the operations team comes in, handles commissioning and startup of the facility. So we can then talk about these phases one by one. We'll not go into a lot of detail. I would only mention the general highlights of the phase, who does what in that phase, and then the kind of deliverables that you expect from each of these stages of the project. First, we'll talk about business appraisal. So, as I've said before, in the business appraisal phase, obviously, is handled by the owner of the facility, who is going to be the operator of the facility. So this business appraisal, the owner is also called the client. For those who are not familiar with this, if you are very new in the industry, the client is the owner. The owner, and of course, the objective of the owner is to develop a sound business case, to be very sure that a business opportunity exists. This is all financial. And then the work done in this stage is useful for, it provides the information that is useful for deciding whether or not to start the project in the first place. Now, from an engineering perspective, not from a business perspective now, but from an engineering perspective, this is the phase where basic data is collected. Basic data / information about the entire project. You collect the data that will help you to make the decisions. So if you're talking about processing facilities like refineries or LNG plants or things like that, facilities that are refining a raw material into a finished product, then we will be interested, the engineers at this stage will be interested in the raw material composition, because the composition has a very significant impact on the kind of facilities that are going to be present in the plant. in the oil and gas plant, if it's a refinery or an LNG plant. One very key thing we look out for is the presence of sulfur, presence of H2S, hydrogen sulfide. So if you have that kind of sulfur in your raw material composition, it completely changes the economics of the project, because the things you're going to put in place to handle to remove the sulfur, basically, because sulfur H2S is highly corrosive to the piping, to the various equipment that will be in the facility. So when there is sulfur present, a lot of facilities, a lot of equipment are put in place to extract that sulfur first. It's one of the key things that we do to purify the raw material in the process of converting the raw material to the finished product. So when we understand the raw material composition, we also think about the product specifications, because the product specification also has an impact on the kind of facilities that you're going to have in your plant. You know, if your product specification is very high grade, then obviously you need some very high tech equipment in your facility to process the raw material to the required standard. So having an understanding of the raw material composition and the product specification puts us in a position where we can know the type of equipment that we need within the facility. Then we also need an understanding of the reaction products and side products in the facility. Yeah. So in the process of converting from raw material to finished product, there are some side products. You know, the reactions will lead to various side products here and there. You know, the process guys will know more about this. So those side products, some of them might have some commercial value. Some of them might be they might have properties like high temperature or maybe very cold temperatures that will have an impact on the type of materials that we would be using for the equipment. And then we have to have an understanding of the utilities and amenities. Utilities are those enablers of the processes. You know, you want to convert your crude oil to kerosene and petrol and diesel and so on, but you need utilities to enable that happen. So in a refinery, you might have utilities like cooling water system. You know, you need cooling water to cool for heat exchange purposes. You would also have electricity. It's a very important utility. Cooling water, electricity, nitrogen that is used for inerting purposes. A whole bunch of utilities are required. So when you have an understanding of the utilities that might be needed in a plant, then it enables you build a better business case. That's for processing facilities. For production facilities, we might be interested in data like the reservoir data, of course, the utilities and the amenities that will be needed, the logistics, because sometimes your oil production or gas production is happening offshore. So you need to envision the logistics for evacuating the product. Are you going to be using maybe subsea pipelines to flow your oil to an onshore location, or are you going to be transferring your fluid, your well effluent directly into a vessel that will then take it offshore, onshore. So the logistics are important. So that's that for the appraisal phase. Once again, this is the complete picture. Appraisal phase, the data you need, and then the next comes the concept selection phase. In the concept selection phase, this is where concept design takes place. Owner's team, the objective is to get the scope of work, to develop a scope of work for the project, and to create a basis of design. Basis of design is very important. I'm going to talk about it again down the line. So this concept selection can be handled by the owner's team, or it can be contracted out. On the projects I've worked on, sometimes the owner's team might not be very experienced with this kind of projects. So they might rely on the services of an external contractor who is specialized in analyzing various concepts and then choosing a particular concept to go forward. Now, when I say choosing a particular concept to go forward, or coming up with various concepts, I'm thinking of a good example to give. Say you have an offshore field. If you have an offshore, I think I'm going to show you an example later. So let me not say too much on that now. The aim of the concept selection study, as I said before, is to confirm feasibility, select a technology, and refine the cost estimate. After, as part of the appraisal phase, the business appraisal phase, there is usually a cost estimate. But because not enough information about the project is known, that cost estimate is very rough. The error margin can be minus 50% to plus 100% if it is done right. So at the end of the concept selection, you expect that that error margin is narrowed down, and then at the end of the feed, it is narrowed down sufficiently for the final investment decision to be made. So here you perform a technical evaluation of various alternatives. I'm going to talk about that in a short while. And then you select one concept and then develop the process design for that concept. Then it is this process design that has been selected that then goes into the feed where all of the various disciplines, come together. So in this stage, for the most part, the process engineers, that's the chemical engineers, work hand in hand with the marketing guys, the business people, to come up with the most ideal financially and technically, or commercially and technically viable alternative for developing the project. So here we expect a class 4 estimate, and then the process design and the preliminary layout of the facility. That is very, very important, because the layout then, the layout is an input to various types of design, the mechanical design, the equipment sizing, and so on. There is a whole back and forth loop between setting out the layout and then setting out the sizes and positions of equipment within a facility. They feed into each other and they take deliverables from each other. In this concept selection, the questions you aim to answer are things like, what is the optimal combination of technologies that is going to achieve the business objectives? I'm going to explain that down the line. What is the optimal utility strategy? For instance, I mentioned that you might be deciding whether to use a pipeline offshore or to use vessels to convey your fluid to shore. You look at technology gaps. In converting your raw material to the desired end product, do we currently have the technologies in the market to do what you want to do to get that required standard? If there are technology gaps, then the project might have to be on hold until those technology gaps are filled by other players in the market. For example, there was a project I was involved with, and at that time, we did not have subsea compression yet. But it was agreed, based on the concept selection, that the only way that project will be profitable is if we have subsea compression. So the company decided to put the project on hold because they knew that other companies were in the process of developing prototypes for subsea compressors. So when those companies develop the prototypes, test them, and they are successful, then you can go ahead with your project knowing that the technology exists to do what you want to do. Then you look at the project economics, of course. Is it going to be profitable? Is it going to be not profitable? You consider the optimal plant location, because this also has an impact on a lot. It can impact the logistics, both for bringing in raw material into the facility and for evacuating the finished product as well. Then you look at the environmental impact assessment. This is also done at this stage because the information about the environment, the required, let's say you look at the government's say regulations about the air quality that is expected in a particular area. If you're going to have a plant in that area, then all of your emissions from that facility have to comply with the requirements of that of the government in that area. So those kinds of considerations would go into this concept selection before you get into the detail, before you get into the feed. You look at the risk of the facility, the risk of the project in general. Are you going to be, how you're going to be impacting the environment, how the environment is going to be impacting the project, how, you know, the market of the plant location, you know, the country where the plant is going to be. You consider all of the risks. Is it a stable government? Do they have political crisis all the time? Is that going to affect your project? You know, do they have, you know, terrorists, kidnappers, you know, various kinds of considerations. All of that is done here. And then we also look at the timeline for commencement of operations. How quickly can we finish the project and start operating? All things considered, after considering everything here, how quickly can the project be completed? Those are the kinds of questions we answer in the concept selection phase. So let's look at a short case study. If you can see the screen here, we have these are three blocks. They are gas fields. This is offshore. This is the shoreline here. And then these are, you can see the contour lines. This tells you this is offshore. So the company owns these three, blocks here. Mr. Nitin, just to confirm, are you there? Can everyone hear me?
Yeah, yeah, it's audible.
Okay, fantastic. So you can see the shoreline. Now, there are various fields. This is field 1, 2, 3, down to field 8. Various fields spread across these gas blocks offshore. Now, the major constraints, as you can see here, number one is that one company owns all of this, but the distance between 1 and 8 is about 400 kilometers. I was part of this project, so I know. So this spread of 400 kilometers, you now start asking the question, how are we going to go about producing gas from all of these fields, you know, knowing that they are all, you know, so far apart, and then they are very far offshore. The distance from shoreline to one here is about more than 100 kilometers. Here to here is almost 300 kilometers. You know, you can see how complicated this is likely to be. And again, all of these fields are in various water depths. The one field 1 here, you can see number 1 here, is around 1,300 meters depth. And then this here is like 2,500, that's number 4. And then number 8 here is around, say, 800. So the water depths are also they vary significantly. All of that information has to be taken into consideration when trying to make a decision on how to progress with this. So the major constraints that accompanied this particular project were that one, the company wanted to use strictly subsea production facilities. So they did not want anything to be on the surface. They did not want any platforms. They wanted everything to be subsea. That's one. You can see that the geographical spread of the reservoirs is also an inconvenience. 400 kilometers between the first and the eighth reservoir is quite a challenge. And then the step out distances, you know, are not the same. The seabed bathymetry is also not uniform. It's not a gradual change in the seabed bathymetry. It's not relatively flat. Some places it goes very deep, this is very steep, and in some places it's relatively flat. So, and then the water depths are not the same. The reservoir depths themselves are not the same. And then, of course, we have other reservoir characteristics to consider, like reservoir pressure, the pressure decline, the pressure decline, um, porosity, permeability, the gross thickness, all of those things have to go into an analysis. And that is actually what we did. We put all of that information in an analysis, and then this was the result. So, sorry, I forgot to mention something else. The aim was to establish a gas plant, an LNG plant. So all of these reservoirs here are gas reservoirs. The target was to take the gas from the reservoirs here, channel it to an LNG plant, and in that LNG plant, of course, process the gas and liquefy it as required. Now, we considered options A, B, C, D, and E as the potential locations for the LNG plant itself. Now, because there are communities around here. We have farmlands, we have fishing communities, and so on. All of that needs to be analyzed, and some discussions with the communities needs to be carried out before you can settle on a particular location as the host community for the LNG plant. Obviously, you want to have a very friendly host community. You don't want a community that will attack your plant every month, something like that. So from all of the analysis that we did, we decided that first we are going to cluster these reservoirs, these fields. So the ones that are in the north, 1, 2, 3, we cluster them together, use subsea pipelines to connect them to a manifold and take them to shore via one pipeline. You can see as it is illustrated here. Then those that are in the south, we do the same thing, link all of them up to a manifold using some short subsea pipelines, and then take this from this point here, take it to shore, and then use an onshore pipeline. What you can see here is an onshore pipeline, 271 kilometer onshore pipeline, and take it to location A. We chose location A as the location for the LNG plant. So you can see that the things that influenced this decision. One, we wanted to minimize the total length of subsea pipelines, because subsea pipelines are very expensive as compared to onshore pipelines. So I think on a rough estimate, if you have a 100-kilometer onshore pipeline and you want to build that same 100 kilometers offshore, it might cost up to 6 times the cost of the onshore pipeline. So whenever you can, you should seek to minimize the cumulative length of the subsea pipelines. Subsea offshore is the same thing. You want to minimize the cumulative length of the subsea pipelines. And then if there is land close by, it is it is commercially wise to use as much of the land as possible, because it's going to make your project significantly cheaper. So you can take a closer look at this, and then I'll go back again. You can see what the challenge was. So we grouped these 3. Mind you that 4 and 5 are not within our scope because they are not owned by the company we were representing. So we excluded 4 and 5. So 1, 2, 3, group them together, take to the location A, then 6, 7, 8, group them together, come to shore, and then use the onshore line to take it to location A. And that's what we did. So we chose the plant location because it presented us with the shortest cumulative pipeline length, and it gave us proximity to infrastructure, because option A is a relatively big town. They have power plants, they have an airport and things like that. So if you're going to have an LNG plant, it makes sense, because this project was in a country where, basically some of the manpower for this project was going to be imported from Europe and so on. So you want a very good international airport when you're expecting, consultants and engineers from places like Italy, the UK, and so on. Locating your project relatively close to a developed city or town makes sense. It doesn't need to be in the center of the city, but at the outskirts. So from the airport, one can easily get there and back. Another consideration was, yeah, I think I've mentioned that already. We wanted to have short offshore pipeline length. So that's the kind of thing you expect to achieve when you carry out a concept selection study. Yeah. Now, the major activities and the major outputs of concept selection. One, the activities include development and engineering. We have development and engineering. That's the process of, playing with the options and deciding what deciding the most economically viable option for coming together or of bringing the various pieces of the project together to have an effective project. Concept selection, technology review. As I said, you have to review the existing technologies on the market to be sure that what you want to do is available. For this project, for instance, because the company wanted everything to be done subsea, and we had, it's not oil, it is gas, right? At that time, subsea compressors did not exist to pump our gas all the way to shore. And at the same time, we knew that the pressure from the reservoir was not sufficient to channel all of our gas to shore. So that obviously was a very big concern for us, which is why we decided to use this clustering system to take advantage of the reservoir pressure to get the gas to shore. Then at shore, we can have this dot here. This, I don't know what color that is, but that represented a plant, a booster station, where we're going to put a compressor that will then compress our gas along this pipeline all the way. Of course, there are going to be other compressor stations along the line, because 270 kilometers is a very long pipeline. So you need more than one compressor station along the way, depending. So yes, we had to do a review of the available technologies in order to determine the best way to go about the layout of the overall project, the layout of the field, and then the layout of even the LNG plant itself. Then the facilities that will be present, the facilities, when I say facilities, I mean the equipment, the kind of separators, the kind of units, like say, the various units in the facility, dehydration units, sulfur removal units, and so on. All of that, the facilities definition is based on process simulation and flow assurance. And then, of course, we look at CapEx and OpEx. Then we talk about risks as well. The major outputs, as you can see here, the basis of design, as I mentioned, and the scope of work. Feed basis of design. This means the basis of design that the feed is expected to follow, and then the scope of work that the feed is expected to execute. Now, these outputs, they are very, very important, especially in a situation where the concept selection study has been carried out either by the owner's technical team or by an external contractor who is not the contractor who will carry out the feed. So, as I said, let's go back a bit again. This. Now, this concept selection study, the owner might choose to outsource it. But then the company that carries out the concept selection study might not be the same company that will carry out the feed. So the concept selection study needs to produce these deliverables that the owner can then hand over to the feed contractor, who will then perform the engineering design of the facility. So that's why those deliverables are very important. Yeah. But in a situation where it is the same company performing concept selection and feed, then there might be less importance on the basis of design and scope of work. Still, they will be needed. They will be part of the project because the owner wants to be sure that the project is being designed according to the right basis. So yeah, they are important, but they are more important when it is two different companies handling it. So if the concept selection is not done right, then it makes sense that from the owner's perspective, you would put extra scope of work for the feed contractor to verify some of these deliverables before they perform their design. They shouldn't just take it and create the design based on that. They should verify that the deliverables that they have received are feasible for the project before they continue. So the basis of design that is produced as part of the concept selection study and the scope of work that is produced as part of the concept selection study, they form part of the contract that the project owner signs with the design consultant, the company that is going to perform the feed for the project. So this basis of design and scope of work, they are part of that contract, so that in signing that contract, the feed contractor agrees to abide by everything that is in the BOD and the scope of work. So going forward, let's look at the design basis. Yeah, I've been talking about design basis. Design basis comes in two categories. We have the design data and design criteria. Now, the design data, I've talked about design data already. The design data include things like the feedstock composition, if you're talking about a processing facility, the environmental data like the wind direction, the nature of the soil, if you are offshore, how much chlorine you have in the water, all those kinds of information that form, that will impact your design. They are part of the what we call the engineering design data. Also included in the engineering design data are the product specification, because you are going to design a facility that is going to convert the input, that's going to convert the raw material to the expected product output. So that product specification is also part of the design data. Then, of course, things like the plant performance, how much uptime do you expect from the plant, 99% uptime, the flow rates, those kinds of things form part of the design data. And then design criteria are the rules that the design is expected to follow. So these two categories of information together form the basis of design. Now, this E here means it is plural. If it was just one, I would have said basis using an I, BASIS. But when I say basis with an E, then I'm referring to design criteria and design data. So in your design criteria, they come in various ways. We have design specifications, we have design philosophies, and so on. Every discipline creates their own process design criteria, civil design criteria, piping design, plant layout. They all have their criteria that they follow, and all that is agreed upon. The criteria that are going to guide the design are agreed by the plant owner, the technical people from the plant owner, and the engineering design contractor. They come together and discuss and agree on the criteria that will be followed, and then they sign, and that then forms the basis of design for the project entirely. So you have your process design basis, mechanical design basis, all of that is combined into one document that is called the engineering design basis or the design specification. So anytime a particular engineer, electrical or piping or mechanical, is performing their work and they have a challenge, there is a conflict, they always refer to the design basis, because the design basis is expected to contain all the guiding principles for the design of the facility. Now, that gives you an idea of how important the design basis is. But then, just to summarize again, the design basis usually includes the project summary. It has all the units of measurements that have been agreed. It might be, for us in Nigeria, we use the metric system. If we are working with, say, an American company that is going to perform our design, we have to agree if we are going to use the metric system or the imperial system. So the units of measurements are agreed between the two parties, and they are part of the, and it's written down as part of the basis of the design. The applicable codes and standards are also agreed upon. The legal requirements for a lot of things, pollution, pressure vessels, and so on. All of that is mentioned. Then environmental pollution requirements as well. Then, of course, in addition to the standard specifications, sometimes a client has their own personal specifications that they want the contractor to follow. So client specifications are mentioned as well. Then feedstock conditions, feedstock composition, all of this is part of the basis of design. The plant capacity, the design and the turn down, the design case and the turn down case, all of that is in the basis of design. The battery limit and battery limit conditions are part of the design basis. The product specification, I've said that over and over again, but I'm summarizing here. The design life of the facility, you also find that in the basis of design. You also find the design criteria per discipline. You also find the outline, that's the operating and control philosophy of the facility. The sparing philosophy, say how much spares should a particular facility have, or a particular equipment or particular component of an equipment, how many spares should they have. Then we look at energy efficiency. You know, all of these kinds of information, the site conditions where the plant is going to be, and so on, the utilities, the infrastructure, shutdown philosophy, the tying strategy, if you're going to have maybe pipelines connecting to an existing pipeline, and so on. All of that is included in the basis of design, which is a major deliverable at the end of the concept selection phase. So just to round up, once the concept selection is done, then we move into the front-end engineering phase. The front-end engineering phase is quite vast. It's where every discipline works together to basically create the facility. So electrical design, civil design, mechanical design, all of that happens in the front-end engineering. And the deliverables that you expect, I've mentioned them already. The feed package, which will include all the PNIDs, the plot plans, the line list, and so on. All of that will, help us create the information that can be used in the final investment decision. So in feed, all of the disciplines are represented, as I've said, but everything is managed by the project management or project engineering discipline. So the project guys are the ones coordinating all the activities of every other discipline here. And you have, just to summarize, this is what it looks like. The process guys, they start, they design the process scheme by developing the process flow diagrams and the heat and material balance, the heat balance and the material balance documents. Then the same process guys use that information to perform process sizing. They use the information from what they have done with the PFDs and the heat and material balance. They also produce the PNIDs, and then they give us the fluid data, the fluid composition. So the equipment sizing, the process equipment sizing is then an input into the equipment design by the mechanical guys. It's also an input into the plant layout by the piping guys. It's also an input into the utility design, which is also handled by process. In fact, the utility design is handled by a multidisciplinary team, but it is led by the process guys. Once the mechanical guys have, finished the design of the equipment, then we can have information like the equipment weights, the equipment sizes, and so on. That is when the mechanical guys will use that. I mean, the civil guys, the structural guys can use that information to design the foundations that will carry those mechanical equipment, your pressure vessels, your compressors, and so on. The foundations must be designed by the structural guys. Underground piping is handled by civil. Underground, in fact, everything underground is handled by civil. Then on this side, P&IDs are used by the piping guys for pipe routing, and then by the instrumentation guys for the instrumentation design of the facility, and then pipe routing. Pipe routing then produces the deliverables that the structural guys will need for designing the pipe racks that will carry the piping. So that's basically how it flows. One last thing here, the fluid data, that's the fluid composition and the condition. When we say condition, we're referring to pressure and temperature, because that can have an impact on the corrosiveness of a particular fluid. So the material selection guys, the material and control discipline, perform the material selection based on the fluid data, that's the fluid composition and conditions that have been provided by the process guys. So all of the coordination of these things, everything happens, some things happen in parallel, some things happen at the same time, but the coordination and the timing of the deliverables from one discipline to another is all managed by the project management guys. So before an engineering project starts in the oil and gas industry, every discipline, all the disciplines you can see here, process, mechanical, and so on, they look at the scope of work and they determine the deliverables they are expected to create. And that leads to the creation of a document called the Master Document Register, or also called the Master Deliverable Register. So the Master Deliverable Register shows the full list of all the documents. Mind you, engineering deliverables always come as drawings or as documents. So drawings, documents, diagrams, that's what engineering deliverables are about. So when you're talking about the engineering phase of a project, you are talking about the process of creating the deliverables that will then be used for procurement and construction. Those deliverables are always in form of documents. So the Master Document Register shows all of the deliverables at any given point in time, and it shows the latest version of each document, because the documents undergo changes as the project progresses. So we want to have the latest document. Let everybody be working based on the latest document. If the process guys have updated the P&ID, then the piping guys need to know that the P&ID has been updated, and they also need to adjust their work to reflect the latest P&ID, something like that. So, when documents are issued, sometimes they are issued for interdisciplinary checks. So a process document can be, like the P&ID, can be checked by the instrumentation and the piping guys to be sure that everything is in order. Then a document can also be issued for client review. It can be issued for design. It can be issued for HAZOP. It can be issued for construction. All of that, all of this is covered in detail in my course, but this is just a summary. The considerations for why a document will be issued for interdisciplinary checks, what goes into a document that is issued for HAZOP, document that is issued for design. I don't want to go into all of those details right now. I've exceeded 1 hour of talking already. So types of deliverables, we have diagrams. Diagrams are, they don't have dimensions. They are just things like block flow diagrams, process flow diagrams, and P&IDs. They don't have dimensions, so they are not drawn to scale. But drawings, on the other hand, are drawn to scale. Examples of drawings are the general plot plan and the equipment layout. These ones are drawn to scale because you want them to go to site at some point for construction. So they need to be drawn according to an actual representation of what will be at the site. And then we have specifications, design specifications, supply specifications, site works specifications, different kinds of specifications. All of the, every discipline has different kinds of specifications. In my course, I discussed in detail from one cost, one discipline to the other, process, civil, electrical, all of them. I talk about all of their drawings, their diagrams, and their specifications. So that's a good point to round up the discussion. Thank you. If you want to connect with me, that's my name on LinkedIn. You can send me an email, thefdacademy@gmail.com. You can also check me out on Twitter.
Okay, thank you, sir, for this informative webinar. I hope everyone got a better understanding of the project management. And now we will open up Q&A session. So all of you, those who have doubts or any questions, can comment down your questions on the chat box.
Should I access the question in the chat box here, or will you read out the questions for me?
You can means actually see the questions in the chat box if anyone puts in.
Okay. Mr. Mustafa Abubakar is asking that one, is the project engineer role more of management or interfacing, or is he required as a subject matter expert in any of the disciplines? That's the first question. And the second question is that after your training, that's the planned one, will one be ready to apply as a project engineer? Okay, so Mr. Mustafa and everyone else who is listening, the role of a project engineer is an interfacing role, yeah? You interface with all of the disciplines. But then, for you to do your job effectively, you need to know what the disciplines are doing. You need to have an idea. You are not expected to be a subject matter expert in all of the disciplines, but you are expected to have an idea of what leads to what. If you look at this, if you look at this chart that I showed here, look at this chart that I showed here. A lot goes into every stage here. It is relevant to have some idea of what these guys do and how the deliverables are important and how they are produced and who needs them and when they are needed. You understand? So you definitely have to have an understanding of what they do. Now, you are not expected to be a process design engineer. You can never know as much as the process guys. You can never know as much as the equipment design guys. You know, if you are operating as a project engineer, you can never, claim to know more than, say, the instrumentation guys about their instrumentation work. But then there are some basic things that you need to know about instrumentation if you are to manage their work properly, if you are to even help them, because they need some inputs from process, they need some inputs from piping, they need some inputs, here and there. So you need to have an understanding of the inputs so that you can then know who to harass in case somebody is, slowing down the job. You understand? So your work is basically coordinating the flow of deliverables, the flow and timing of the deliverables. But then having an idea of how those deliverables are created and the amount of work that goes into it goes a long way in helping disciplines about what they do so that you can manage them properly. And then my planned training, yes, it discusses every discipline in as much detail as I can as a project engineer who has some experience doing these things. So yes, you will be able to apply as a project engineer after you take my course. And somebody is asking, that's Shedrack Edema, what marks the end of detailed engineering design? When you say detailed engineering design, from my experience, we have the EPC contractor is responsible for the detailed engineering design, not the basic engineering. So this basic engineering, that's the feed that we have I've tried to talk about, and that is covered in my course. This feed is what gives the deliverables that the EPC contractor can use to perform detailed engineering. I will not say there is a specific end for detailed engineering. Why? Because procurement is already ongoing. By the time you say you complete engineering, you have ordered for some pipes, then you do some further design work, you update your design, then you do some more design work and you update your design. If there is anything that can signify the end of engineering, I would say is the third 3D model review. When you are designing the facility, you are creating a model of the facility in a computer, right? So there is a first stage model review. When you have designed 30% of the equipment and piping of the facility, you perform the first stage model review to confirm the plot layout of the plant. Then, as design advances, at some point, you would have completed 60% of the design and the modeling. You now review the model again. Then you progress again, and then you perform the 90% model review. That's the third stage model review. Yeah. So this third stage model review, you perform it at the point where almost all engineering work has been completed, almost all. But I cannot say that it marks the complete end of engineering. No. So the end of detailed engineering design, I'm not sure there is a specific end, because even when you start construction, some engineering is ongoing. The civil guys might be at site performing, some construction work and so on, but then some engineering work might still be ongoing. It might still not be completed yet. In fact, your 90% model review, by the time you are performing the 90% model review, you have advanced with your site work to an extent, maybe up to 20 to 30% of your site construction. So a lot of things happen in parallel. Shadrach, I don't know if that sufficiently answers your question. But then if it doesn't, you should ask again. I'll proceed to the next question. Mr. Sheriff Raji is asking, I noticed the activities of project engineers are not as pronounced in the design stage, unlike the construction stage. I think it depends, yeah? It really depends on the way the company is handling things. Project engineers are quite important in the engineering stage. That's in the design stage. Now, you know that in the design stage, there's usually an engineering manager. So the engineering manager is responsible if there are project engineers on a project, and there is a that's on a design project, and there is also an engineering manager. The typical situation is that the project engineers are usually working under the engineering manager. So they help the engineering manager with various aspects of the job. But there are some projects where there is no engineering manager, and the project engineer is the one performing the role of the engineering manager. And different companies have different names. An engineering manager in one place can be senior project engineer in another place, or a senior project coordinator or something like that. The terminologies might vary, but the important thing is that there is somebody, whether you call that person an engineering manager or a project engineer or a project coordinator or anything you can come up with, the important thing is that the job of that person is to coordinate the flow of deliverables from one discipline to another. At site, hmm, again, I am talking from what I consider to be a standard way of doing things. I cannot talk on behalf of every company. But then at the end of engineering, the engineering company is expected to send a team to the construction site. That is the field engineering team. Now, I don't know what different companies might be referring to as a field engineer, but from this perspective of the conversation that we're having today, the field engineer is an engineer from the design consultant who understands the design, who was part of the design from the beginning, understands the deliverables, and has the capacity to perform the same engineering design job at site. So they are there to correct, some design or errors that might be encountered at the site. For example, if in the design there is supposed to be an equipment foundation somewhere, but during construction, it is realized that, that equipment foundation was cast in a slightly, shifted position from where it is supposed to be. A foundation is usually quite expensive. So instead of removing the foundation and recasting it, the field engineers might be responsible for redesigning the piping that is supposed to connect to the equipment that will sit on that foundation, a reorientation of the equipment. It is cheaper to do that than to recast the foundation. So at site, you might have field engineers doing this, but then your company might be calling them project engineers or construction engineer, or different kinds of terminologies that vary from company to company. But then the engineers that are familiar with the design, who are present at the construction site to help with engineering design challenges at the construction site, are called field engineers. I don't know if that answers your question, and I don't think it was a question, it was a statement, but I felt it should be responded to. How is an engineering manager selected? Obviously, an engineering manager will be somebody who has experience in various disciplines. Now, I'm not saying that he has to be an expert in mechanical and civil and so on. No, an engineering manager always, as all of us, we studied engineering in one field or the other. My background is that of a civil engineer, but right now I can function as an engineering manager because of my experience. I have been in a position where I have coordinated the activities of all these other disciplines. So that experience is what prepares you to be an engineering manager. So if you are a mechanical engineer, you need to have worked on this kind of project before. You need to have interfaced with the process guys for some years. You need to have interfaced with the instrumentation guys to understand what they do. You need to have interfaced with the electrical guys. When you have interfaced with them, working with them, doing engineering reviews with them for a long time, over time, you develop an idea of what they do, and it can help you manage their work. So at that point, you can be an engineering manager, but you cannot just come fresh from school or being in one discipline without interfacing with other disciplines and then be an engineering manager. That will not work. So I would say an engineering manager is selected based on his experience in handling the coordination of the activities of the various disciplines. So if you're a project engineer, you can either your career can take you to be an engineering manager, or it can take you to be a project manager, or you can do both. Sometimes you work with somebody on a particular project. The person is a senior project engineer. The person moves to another company, is an engineering manager there. Then he moves to another company, is a project manager. Then he moves to a different company and is an engineering manager again. Once you have the experience, the title doesn't really matter much. Mr. Mayowa, thank you. You said this is really educative. Thank you, I appreciate. I noticed the activities of project engineers. Okay, that is a repetition. Some companies depend on document controllers for interface management of the disciplines during um, document controllers. They are responsible for producing documents. I mean, they are responsible for channeling documents to the right destination. They are not responsible for, say, they don't contribute to developing the project schedule, for instance. A document controller will not be there when we are discussing the timeline for the project. So, but then you can have the project engineers there, you can have the project manager there, you can have the engineering manager there. The document controller is only is a conduit for channeling the deliverables to the right destination after the deliverables have been produced. It is not the document controller's responsibility to demand the quick creation of a particular document. That is the job of the project manager, project engineer, or the engineering manager. So don't confuse what document controllers do. If a company chooses to depend on a document controller to perform interface management, that would be quite strange to me because they don't have the capacity. They don't have the capacity to do it. I mean, a document controller can be somebody who has an accounting background. He doesn't need to be an engineer, but a project engineer needs to be an engineer. Interface management, as far as the engineering phase of the project is concerned, interface management should be handled by somebody who has a technical background. And shipping one document from, say, process to instrumentation is not interface management. That's not it at all. So that's for Mr. Sheriff Raji. If you agree with me, you can comment. So Mr. Mustafa is interested in the training. Thank you very much. You can send me an email. Let me put my screen, my email. Oh, sorry. That's my email address. So you can send me a message and then I would inform you when the course is launched. Can I know, that's Sibyl Samuel, can I know the cost, the time, and whether or not there will be a certificate for the course? So the course is a pre-recorded course. It's pre-recorded. It will be online, a series of videos. You will watch the videos, and at the end, you will get a certificate automatically. The videos are hosted on a platform that will force you to watch every single video to the end before you can get the certificate. So you are not going to be permitted to skip from the beginning to end and just download the certificate, because it is knowledge I'm sharing. It's not certificate that I'm sharing, but I know that people want to have certificates and they will appreciate getting a certificate. So the certificate is present at the end. It will carry your name and you will be able to download it in PDF format, but you have to go through every video before you can get to it. That's for Sibyl Samuel. And Doze, what role will a PM with a civil engineering background, certified PMP, but not a licensed current member? So I am a civil engineer. I have PMP. I got my PMP 10 years ago. My current certification came only 2 years ago. Now, maybe I was lucky. I never really considered the current thing too much. But eventually, at a particular stage of my career, I decided it is time. So some companies can pick you up and give you the opportunity without necessarily requiring you to be current certified. If you have the knowledge, if you display the knowledge at an interview, then definitely you can be given the job of a project engineer. Becoming current certified is not very, very difficult, So that's something you should look into. If you have the funds to pursue it, you can go ahead. It's a Nigerian certification. For those of us who are listening who are not from Nigeria, current means the Council for Regulation of Engineering in Nigeria. So it might not be relevant if you are not a Nigerian. But if you're a Nigerian, you can pursue current certification. But experience comes first. Even the current certification is a test. The current exam is a test of your experience. So if you don't have the relevant experience or the relevant knowledge, you might not pass the exam and you might not be current certified. So regarding certificate, this was the free. Oh, yes. This conversation that we are having here is not a course. It is just us discussing some concepts that some people might not be familiar with in the industry. So there is no certificate at the end of this particular discussion. This is not it's just a webinar. It is not a course. It is not a certificate course. Okay. If you have heard me talk about a certificate, it is for my own course that I am creating. And if you send me an email, using this email here, you would be able to reach me and I'll tell you when to enroll. Yeah, Lydia, thank you. Okay, Sheriff agrees to my answer before. This session is recorded. You can re-watch it. Oh, good, nice. Ifenkwe, I'm a materials and metallurgical engineering graduate interested in project management. I developed this interest after my undergraduate internship in the production, planning and control department of a construction firm. Currently, I am taking free online courses on project management and learning to schedule projects with Microsoft Project. What is your advice? So it is good to have theoretical knowledge of projects so that when you get an opportunity, you will hit the ground running, so to speak. So I advise that you, first of all, if you're not working in a company where you are in a project management position yet, I would advise that you get as much theoretical knowledge as you can. Eventually, that knowledge is going to become useful. You are going to be applying for project engineering roles, junior project manager roles, and so on. It also helps when you have a certification. Like my course is going to help you part of the way. Also, for general project management, there is the PMP certification, but that one is for experienced professionals. And then there is the CAPM, Certified Associate of Project Management. That one is for people who do not have experience. So you can take the CAPM certification exam. I also have a training for that. So if you're interested in taking the CAPM certification, you can send me an email and you can send me an email and then we'll talk about how I can onboard you on my CAPM preparatory course. I also have a PMP training course. So if you have the experience and you want to become PMP certified, I also have a training for that. And you can send me an email once again and I can put you through. So that's that if you have no further questions. For those who are interested in oil and gas project management, you will benefit from my course. For those who are interested in general project management certification, either PMP or CAPM, I can help with that as well. So if you have further questions about project management in the oil and gas industry, I am all ears. Otherwise, I would hand over to Mr. Nitin.
Okay, I believe that this is the end of the session. So thank you so much, Mr. Du, for the session, and thank you all for joining us here. Remember that the session will be available on our YouTube channel. that is of Scholar Gates and Petronile Academy, and you all can rewatch it. So we will end up the session right here. Thank you so much. Stay safe,
All right.
everyone, and goodbye.
Yeah, thank you, everyone.